Hello, today we're going to be talking about the energy, intensity, and pressure of electromagnetic radiation. Uh, Light is one form of electromagnetic radiation, and you know that the light from the sun delivers power to the earth because it heats up the earth and feeds the plants and powers solar panels and so on. And power is energy per unit time. And the power that's distributed over the area that it shines on is called intensity, and it has the symbol I. And I'm sorry, I know that's confusing. We've been talking about current that has the same symbol. Pretty much from now on, we're going to be using I for intensity instead of current. So intensity is power, the average power per unit area. And for sunlight on Earth, that's about 1,000 watts per meter squared. So the question is, how do we relate intensity I to what we've been talking about for the past 4 chapters, which is electric and magnetic fields? Well, the answer is the Poynting vector, and it's spelled a little differently. It's not P-O-I-N-T-I-N-G, but it's strange because it really points in the direction of propagation of an electromagnetic wave. And remember our last lecture we said that we can use the right-hand rule with electric and magnetic fields, which are perpendicular to each other, to determine the direction of propagation of a plane wave. So if you put your fingers in the direction of E, and your palm faces in the direction of B, then your thumb points in the direction of propagation. So your thumb points in the direction of the Poynting vector. Poynting vector points in the direction of propagation. The magnitude of the Poynting vector is equal to the intensity. The average value of the Poynting vector is equal to the intensity. So that's the relationship between electric and magnetic fields and the intensity, like the sunlight that we actually feel on the surface of the Earth, for example. So we have this formula for Poynting vector S, and we know that electric and magnetic fields are a solution to a wave equation, and the solution to a wave equation involves a sine or a cosine, kx minus omega t. And if I plug these in to my Poynting vector equation, I get EB sine squared kx, so kx minus omega t divided by the permeability of free space. And if I average a sine squared function over one period, remember we get 1/2. I think we showed that graphically a couple lectures ago, or you can do it using a trig substitution. So this expression simplifies to just 1/2 EB over mu naught when you look at the average value of the Poynting vector, which is equal to the intensity. And also remember from last lecture, when we plug these equations for E and B into the wave equation, we get this relationship between the magnitude of E and the magnitude of B. It's just the speed of light. So this is just like the velocity selector that we talked about in mechanical waves chapter. Okay, so these three will be useful to remember, that I is equal to CB squared over 2 mu naught, or E squared over 2 mu naught C. Let's do an example. Let's estimate the magnitude of the electric and magnetic fields from a 60-watt light bulb shining on your paper. And the light bulb has a certain inefficiency. It's not all of the power, not all of the IV power that goes into the light bulb gets transmitted into light energy. In fact, only about 5% of it does. So you might be tempted to take that power, that's going to be 3 watts, right? 60 times 0.05 is 3 watts, to divide that power by the area of your piece of paper, but that wouldn't be right. We have to remember that the light bulb is a point source, or we can model it like a point source, that transmits its energy equally in all directions. So that means it transmits its energy equally over the surface of a sphere that has a radius r, for example. So the area of a surface of a sphere with radius r is 4 pi r squared. So to get the intensity, I take that power, the 3 watts, divided by the 4 pi r squared area of that sphere. That gives me the intensity on my paper. For the radius of the sphere, I use the distance from the point source to my paper. So in this case, I'm saying it's 30 centimeters away. All right, once I have a value for I, then I can use these equations to get either the magnitude of E or the magnitude of B. Decided to just get the magnitude of B first. So plugging in 4 pi times 10 to the minus 7th for mu naught, and 2.65 for intensity, and 3 times 10 to the 8th meters per second for C, the speed of light, I get 150 nanoteslas, and I put some comments down here to help you work out the units because they're a little tricky. And now one way to solve this would be going back to these equations and solving this for E, right? This would be E naught equals the square root of 2 mu naught C times I. But it's easier, I think, just to take the result that we got and divide it by, or multiply it by C. That will give us the magnitude of the electric field. So it's interesting, there's about 10 to the 9th order of magnitude difference between the two. The electric field has much higher magnitude than the magnetic field. Okay. The next thing I'd like to talk about is radiation pressure, which has very little to do with optics. We're not going to be seeing this again most likely, but I wanted to mention it because it's actually really cool. And there's something that happened pretty recently. A couple of years ago we had this flyby of this gigantic looking potato thing, and for a while people thought it was well, in fact, one famous physicist, the department head of Harvard's astronomy department, actually still thinks that it's a remnant of a solar sail from another civilization. And the reason for that is because it's accelerating, right? It flew by the Earth at this really high rate of speed, but then as it was moving away from the sun, it was accelerating. Well, how do you explain that? Right? As it's moving away from the sun, the gravitational attraction of the sun should be pulling it back towards the sun, so it should be decelerating. Instead, it was accelerating. How is that possible? Well, one possibility is that it really was using the radiation pressure of the sun. Well, maybe that's a strong way to say it. One way to explain it is that the radiation pressure of the sun was causing it to accelerate. And one person suggested that it was actually a solar sail from another civilization. It came from somewhere around Vega, if you know where that is. It's one of the brightest stars in the sky. Alright, so Einstein said energy equals mc squared. Instead of E, I'm just going to write out energy. And we know that, and I can write this as the product of mass times the speed of light times the speed of light. And remember that mass times velocity is momentum. So this is another way of saying momentum, mass times velocity. So I can write E, instead of energy equals mc squared, I can say energy equals momentum times the speed of light. And we know light transmits energy, so if I solve this for momentum, I get momentum equals energy divided by the speed of light. And that's not equal to zero, right? Because energy is not equal to zero, C is not equal to infinity. So that means that the momentum is not equal to zero. That's a mind-blowing thing in itself, right? Photons have no mass, and yet they have momentum. And the momentum is given by the energy divided by this expression, energy divided by C. And I know from Newton's second law that force is equal to the time rate of change of momentum. Remember, you might be more familiar with F equals ma, but acceleration is dv dt. So m dv dt is the same thing as the time derivative of mv, which is momentum. So F equals dp dt is just another form of Newton's second law, and I'm going to substitute P equals energy divided by C for momentum, and now I'm using the symbol U for energy, and we remember that energy per unit time is power. So the force exerted by electromagnetic radiation by photons is power divided by C. Well, we know pressure is force per unit area, so if I divide this expression by area, now I have power over area, which we know what that is. That's intensity. We even have a number for it, times 1 over C. So that tells me that the radiation pressure, when I completely absorb the photon, is just the intensity of the light divided by the speed of light. That's the radiation pressure. And, I didn't use P because we're using P for 3 different things in this chapter. P for radiation pressure, P for power, P for momentum. So that's why I'm writing it out each time. So let's talk about what happens if it bounces. Remember from our conservation of momentum discussion last semester, we know of, for example, if you're throwing a baseball and the batter hits the ball back, now you've got twice the momentum change. You've got the ball coming in at one speed, the ball leaving at the other speed. You have to take the difference of those, but they have different directions. So you have a minus situation. So now you have twice the change of momentum that you would than if the photon was completely absorbed. So the radiation pressure when the light is completely reflected is twice the radiation pressure when it's completely absorbed. So it's 2I over C instead of I over C. So we'll look at one example, and that's let's try to figure out the power, pressure, and force of sunlight on the roof of the Science Center. And the roof of the Science Center is approximately 30 meters wide by 80 meters long. So to calculate power, I remember that intensity is power divided by the area that the power is distributed over. And the intensity of sunlight at the surface of the Earth is about 1,000 watts per meter squared. So if I multiply both sides by area, I get power equals intensity times area, which is 2.4 megawatts, a really big number. Right? It's easy to understand how you can draw a lot of energy using solar panels if this type of energy is available just on the surface of the roof. And to figure out the pressure, remember radiation pressure is intensity divided by the speed of light. So this is intensity, that's the speed of light, and that gives us a very small pressure of micropascals. And here I just wanted to make sure that the units worked out, and they did, right? Because a watt second is a joule, and a joule is a Newton meter. So a Newton meter divided by meter cubed is a Newton per meter squared, which is a Pascal. And then finally, let's figure out the force, remembering that pressure is force per unit area. If I solve that for force, I get force equals pressure times area. So I take this minuscule pressure, I multiply it by the pretty big area on the roof, and I get 8 millinewtons. So it's a very small force. But if you are in the empty vastness of outer space and there's no mass around to slow you down, and you get hit with an 8 millinewton, with 8 millinewtons worth of photons, eventually you will see that speed difference, right? Your acceleration might be really slow if you're massive like the Oumuamua asteroid, but you're going to accelerate because there's a non-zero force on you from the radiation pressure from the sun. That concludes our discussion for Chapter 24. Please don't hesitate to call or text if you have any questions.